Welcome to Lecture 17. We're going to begin a brand new topic now called Multiplexers. But before we do, I would like to review the final problem from our last test, Test 15, because it seemed that problem challenged more people than some of our previous problems had. And so I just want to make sure that everybody has a clear understanding of how to do that problem. So we'll just say review. The problem is as follows. It says that f, the function f of a, b, c, d is equal to the sum of the min terms 4 and 15 with don't care conditions for 0, 1, 5, 6, 7, and 10. And we're told that this has two minimal sums. And the question was to list all cells in the K-map in which these two minimal sums have different values. And so I want to go over this problem very thoroughly and make sure that everybody has a clear understanding of it. So f is a function of 4 variables, and therefore there are 2 to the 4th, or 16 cells in the Kernel Map. And so let's go ahead and draw the Kernel Map. Okay, so here's our outline of the kernel map, and the only cells in which we have ordinary ones are cells 4 and 15. So recalling the usual way to count now, this is 0, 1, 2, 3. So here's cell 4, and it gets a 1. And then continuing 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and here's cell 15, and it gets an ordinary 1. But we do have don't care conditions, which will get the squiggly ones, if you wish, or just some kind of symbol to help you remember that they are not ordinary 1 cells. So cell 0 gets one of the squiggly ones, and likewise for cell 1, and likewise for cells 5, 6, and 7, and that's here's 5 and 6 and 7, and then finally cell 10, which is down here in the lower right hand corner. So this is the kernel map for this function, and now we'll proceed. As usual, the first thing we'll do is to find all prime implicants, because after all, if we're going to answer this problem, we need to identify these two minimal sums that we're told that this function has, And then we can, once we've identified the two minimal sums, then we can find out in which cells these sums differ. So to find the minimal sums, we want to first find the prime implicants. We don't have any rectangular groupings of 16 one cells or any rectangular groupings of 8 one cells. However, we do have some rectangular groupings of 4 one cells. And so let's tackle those. One obvious grouping of a rectangular grouping of 4 one cells is here in the upper left hand corner, and the name of that is A prime C prime. Another grouping, rectangular grouping of 4 one cells is there. And that is A prime B. Now, if you continue to look, I believe that you'll conclude that there are no more rectangular groupings of 4 one cells. So next we go to rectangular groupings of 2 one cells, and we do have one here. And if you look at for the name of that, you see that it is B, C, D. And after that, there are no more rectangular groupings of 2 one cells, and so now we look for single one cells, and of course we do have one down here in the lower right hand corner. And that is A, B prime, C, D prime. So that concludes our list of prime implicants for this problem. And now we want to determine which, if any, of those prime implicants are essential. And the way that we do that is by first identifying essential one cells. So as we start here on the top row, we see that neither one of these one cells is essential, simply because those are don't care conditions, and don't care conditions can never be essential. This one cell is not essential because it is contained within more than one prime implicant. The rest of the ones in the second row are not essential for sure because they are don't care conditions. Likewise, this one cell down here in cell 10, it's certainly not essential because this is a don't care condition. So the only remaining one cell that could be essential is this one, cell 15, and in fact it is essential because we see that this one cell is contained within only one prime implicant, and that is the prime implicant right here, which our picture reminds us is the prime implicant BCD. So our only essential prime implicant for this problem is BCD. And now that we've identified that, we're ready to try to find now all minimal sums. And since the problem has told us that there are 2 of these, I'm going to go ahead and write down f of a, b, c, d twice. Now we know that every minimal sum must contain all of the essential prime implicants, and therefore, since BCD is the only prime implicant in this essential prime implicant in this problem, then it must be in both of these. So we have BCD and BCD. And now we ask ourselves, what else must be added in order to account for this entire function? So let's go ahead and shade in what we've accounted for, and that is the sole prime implicant here, the sole essential prime implicant, BCD. So we shade that in. And once we do that, we realize that there's only one more thing here in the function that has to be accounted for, and that's the 1 sitting right here in cell 4. Everything else is don't care conditions, so we really don't care if those are 1s or 0s for all these squiggly marks. It's just this that we want to make sure is a 1, and we include that. And there's 2 different ways that we can do it. We can include this prime implicant, A prime C prime, or we can include this prime implicant, A prime B. And so those are our 2 minimal sums, BCD or A prime C prime is 1, and the other one is BCD or A prime B. And you see that these 2 minimal sums both have 5 literals. You see here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So both of them have 5 literals. They're equally simple, and so both of them must be included. So those are the 2 minimal sums. And now we get to the actual question, which is to find all the minimal cells, find all the cells in the kernel map in which these 2 minimal sums have different values. Now, keep in mind here that for this first one, this is the one that has the essential prime implicant. Of course, both of them have the essential prime implicant, but it has the essential prime implicant here, and it has also this prime implicant. So it does not include this squiggly 1 in the lower right hand corner, nor does it include this squiggly 1. On the other hand, the second minimal sum is this essential prime implicant and this prime implicant, so it does not include these 2 squiggly 1s or the squiggly 1 in cell 10. So we can conclude all of that by saying that neither minimal sum includes this don't care condition down here in cell 10. So the minimal sums will both have 0 value there. Since they don't include that, they will both have 0 there. However, the first minimal sum includes these 2 cells, so it'll have 1s there, but it doesn't include that, so it'll have a 0 over here in cell 6. On the other hand, the second minimal sum does not include these 2 cells, so it will have 0s in cells 0 and 1, but it does include this, so it'll have a 1 in cell 6. So there are 3 cells in which these 2 minimal sums are having different values, and those are cells 0, 1, and 6. So we say these minimal sums have different values only in cells 0, 1, and 6. And just to really drive home this point, even though it is a little bit tedious, I want to do the Karnaugh map, the truth table for both of these minimal sums, and just really prove that these are the only cells in which they have different values. So we'll go ahead and put our 4 independent variables. We want that, and then we'll say BCD and A prime, C prime, and A prime B, and then we'll say first minimal sum and second. minimal sum. And actually, for the sake of convenience, I think I'll actually change the order of these columns. You'll see, if you don't see now why that's more convenient, you'll see in a few moments. So I'm going to say A prime, C prime, and then B, C, D. I'll put the columns in that order. And so now, let's begin to fill this in. Oh, this is terrible. Sorry about that. Okay, so there are our rows. We have here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So those are our rows. And now let's go through and compute these other columns. So A prime, C prime, well, in the first row, since A is 0 and C is 0, then A prime will be 1 and C prime will be 1, and so this will have a value of 1. And likewise in the second row, A is 0 and C is 0, so A prime is 1, C prime is 1, and 1 is 1. In the next two rows, C is equal to 1, which means C prime is equal to 0, and 0 ANDed with anything is 0, so we get 0 in the next two. And then in the next two, we're back to A and C are both 0, so A prime and C prime are both 1, and 1 ANDed with 1 is 1. The next two rows after that have C equals 1, which means C prime is equal to 0, and 0 ANDed with anything is 0, so we have 0 in these two rows. And then in all of the remaining rows after that, A is equal to 1, which means that A prime is equal to 0, and 0 ANDed with anything is 0. So we can go ahead and fill in the rest of the rows very easily. Okay, now for BCD. Well, clearly this is equal to 0, 0, 0, 0, 0, 0, 0. But here in this row number 7, where A is 0 and B, C, and D are all 1, then BCD will be 1. And continuing down, we get zeros in all of these rows until we get down to the very bottom, where in fact all 4 variables are 1, and so BCD is 1 there. Now, remember that our first minimal sum is BCD ORed with A prime, C prime. So our first minimal sum is the OR of these two columns that we've just written down. So if we OR these two columns, we get 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, and 1. And that identifies the value of the minimal sum for every possible combination of the variables a, b, c, and d. And now we want to do the same for the second minimal sum, but before we can do so, we need to find a prime b. So let's do that. Wherever b is equal to 0, this is going to be 0, so we get in the first 4 rows, we get a 0. Wherever a is equal to 1, this is going to be 0, because if a is 1, then a prime is 0, and 0 ANDed with anything is 0. So in all of these rows down here, we get a 0. And now in all of the remaining 4 rows here, a is 0 and b is 1. And since a is 0, a prime will be 1. So we get 1 ANDed with 1. So we get 1s in all of the remaining rows. And now, if we will look at these 2 columns right here, remember our second minimal sum, we want to fill in that column, and our second minimal sum was BCD or A prime B, and that's these 2 terms here, so we just need to look at these 2 columns and go down the different rows. So we get 0 when we OR these 2 together, when we OR these 2 together, or these 2 together, or these 2 together, we get 0 in all 3 of those cases. And then continuing, when we OR these 2 together, we get 1. When we OR these 2, or these 2, or these 2, we get 1. So 1, 1, and 1. Continuing, when we OR these, 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 we get 0s in each of those cases. But when we OR these 2 columns here, in this final row, we get 1 ORed with 0, which is 1. So that completes the second minimal sum. And now we want to compare the value of the first minimal sum with the value of the second minimal sum for every combination of the variables. And we'll put check marks by those situations where they differ. Well, clearly, in this first row, they have a different value, so we'll put a check mark. In the second row, they have different values, so we'll put a check mark there. In the third row, they have the same value. Fourth row, they have the same value. Fifth, here they have a different value. And continuing, same. So the 2 minimal sums differ in 3 situations, and that is 0, 0, 0, 0 for A, B, C, D, which of course corresponds to cell 0 of the K-map, 0, 0, 0, 1, which corresponds to cell 1 of the K-map, and finally down here in this situation as well, which is 0, 1, 1, 0, which corresponds to cell 6 of the Kernel Map. So by looking at the Kernel Map, we were able to get all of this information. It was not at all necessary to do the truth table, but I just wanted to really prove to you that what we had done was correct. And so that is the way to do the kind of problem that you saw at the end of test 15. And so now we're ready to begin a brand new topic, which is multiplexers. The simplest multiplexer is called a 2-to-1 multiplexer, or for short, we just write MUX. And the symbol for this device is as follows. So we have one output Z, and in the case of a 2 to 1 mux, and by the way, we usually will say 2 to 1 mux here. So we have one output variable Z and three inputs, I0, I1, and A. And the idea behind the way the mux works is that the value of A determines which of the two inputs, I0 and I1, will be selected for the output. In other words, when A is equal to 0, then I0 will go to the output. And when A is equal to 1, I1 will go to the output. So let's write that down. When A equals 0, Z is equal to I0, and when A equals 1, Z equals I1. So if we wished, we could actually draw a truth table for the output as a function of the three inputs A, I0, and I1. It would go like this. Let's say A, I0, and I1. So, and then Z is our function we're interested in. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And remember, in all the cases where A is equal to 0, Z is equal to, as we said here, when A is equal to 0, Z is equal to I naught. So in the first four lines, where A is equal to 0, Z will simply be equal to I naught. So it will be 0, 0, 1, 1. But in the second four lines, when A is equal to 1, then Z will be equal to I1. And so 0, 1, 0, 1. And that would be the truth table for Z in terms of A, I0, and I1. If we think of min-term expansion for Z, we could do that as well. Remember that when you want the min-term expansion, you want to get the min-term expansion from the truth table, you simply look at when the function is equal to 1. And we get that Z is equal to 1 in these two rows and in these two rows. And so I hope that you will agree that we should write down for the min-term. Well, try this. Certainly try this yourself first. You should definitely be able to do this. Take a minute to try to do it yourself, and then resume the video. Okay, so I hope that what you've concluded here is that this first one is the term A prime, I0, I1 prime. The second one is A prime, I0, I1. The 0 down here is A, I0 prime, I1. And then the final one is A, I0, I1. So this would be a way for the 2 to 1 multiplexer. This is a functional expression for our output Z in terms of the three inputs A, I0, and I1. Now you might say, well, is this the simplest sum? Notice that this is a SOP expression, as is any min-term expansion, but is this the simplest sum that we can get? So let's find all minimal sums. Now again, this is something that you definitely should be able to do, so I strongly encourage you to stop the video, try to do this yourselves, and then resume and see if you got the right answer. Okay, Z is a function of 3 variables, so we have a kernel map with 8 cells. And we'll put A on the vertical axis, and I0 and I1 on the horizontal axis. And the first term here, A prime, I0, I1 prime. Okay, since it says A prime, it'll be in the first row. And I0, I1 prime means 1, 0. So we have a 1 here. A prime, again, this will be in the first row of the kernel map because of the A prime. And we have here I0, I1. So that's 1, 1. The next one, since we have A, will be in the second row of the kernel map where A is equal to 1. And here we'll have 0, 1. And this one will be the second row of the kernel map, 1, 1. So, like this. And this is the kernel map for the function Z in terms of A, I0, and I1. And now that we have the kernel map, we can look for all minimal sums. As usual, our first step will be to find all the prime implicants. There are no rectangular groupings of 8 or 4 one cells, but there are rectangular groupings of 2 one cells. One is here. And that is the prime implicant A prime I naught. Another rectangular grouping of 2 one cells is here. And that is the prime implicant I naught, I1. And then a final prime implicant of size 2, and in fact the final prime implicant of all is this one. And the name of that will be AI1. And that completes the prime implicants of size 2, and there are none of size 1. So that's all of our prime implicants. And now, as usual, we want to know if there are any essential prime implicants. And so we look for essential one cells, and this one cell here is essential, as is this one. The 2 other one cells are not essential because both of them are contained within 2 prime implicants. So this essential one cell on top is in the prime implicant A prime I naught, so that prime implicant will be essential. And the essential one cell here in the second row is in the prime implicant AI1, so that is essential. So our 2 essential prime implicants here are A prime I naught and AI1. And so now when we get ready to conclude the problem, we can say that Z is as usual, we have to start with what's essential. So we have A prime I naught or AI1. And now we need to ask ourselves if anything else is needed. So let's shade in those 2 terms, the A prime I naught is here in the upper right hand corner, so we'll shade that in since we have included it in the minimal sum. And AI1 is down here in the middle of the second row. We need to shade it in. And now we ask ourselves if anything else needs to be included, and the answer is no, because we've accounted for all the ones in this function, and therefore that's it. There's only one minimal sum. So this would, although this up here, this expression is this expression here is the minterm expansion for z, and it is a sum of products expression, but the minimal sum expression for z is shown here. Z equals a prime I naught or a I1. Now, in addition to 2-to-1 multiplexers, there are also 8-to-1, 16-to-1, 32-to-1, in fact 2 to the n to 1 multiplexers. And just to drive this point home, let's look at one more example. We won't do all the same work that we did for the 2-to-1 multiplexer, but let's at least look at the symbol for the 4-to-1 multiplexer. So this would be the symbol for the 4-to-1 multiplexer, and notice that since there are 4 input lines here, then we need 2 select lines down here, A and B, in order to select which of these input lines will be output over here at Z. And as you would probably expect, when A and B are both 0, that selects line 1, it selects this first line, which is I0. When we have 0, 1 for the select lines, down here, 0 for A and 1 for B, then we will select I1. When we have 1, 0, 1 for A and 0 for B, we select I2. And when we have 1 and 1, we select I3. So it really is just like the 2-to-1 multiplexer, except now we have 4-to-1, so we have 4 of these input lines, 2 select lines, and then 1 output. If you think carefully about this, you might be able to see that the way that we can write Z, a minimal way now in which we can write Z as a function of all of these inputs, I0, I1, I2, I3, A, and B, is as follows. Okay, let's start by saying A prime, B prime. Now that will only be equal to 1 when both A and B are equal to 0. But when A and B are equal to 0, we said we want Z to be equal to I0. So we'll have this. Next, we'll say A prime B. This will only be equal to 1 when A is 0 and B is 1. But when A is 0 and B is 1, we want the output to be equal to I1. So we'll do this. And continuing with this same kind of thinking, we get the following. Okay, so now let's review this. you can see that when, in each case, we start off with A and B, and we're covering all four possibilities, A prime, B prime, A prime, B, AB prime, and AB. When A and B are both 0, we're going to get this first term, and so that's why we multiplied or ANDed that with I0. When A is 0 and B is 1, we'll get this term, so we ANDed it with I1. When A is 1 and B is 0, we want I2, so that's what we've put there. And then when A and B are both 1, we get this. And you can notice that this is very similar to what we did before with the 2-to-1 multiplexer. Remember, when A is equal to 0, we want the output to be I0, and that we fix that by putting A prime I0 here, because when A is equal to 0, that'll be 1. And when A is equal to 1, we want the output to be I1, so we have this. But the only difference now is that with the 4-to-1 multiplexer, of course, we have 2 select lines and 4 possible input lines. So this would be the minimal sum. Now, we didn't prove it as we did in the 2-to-1 multiplexer case. You could easily do it. It just becomes a more tedious problem. But this is the way that we would do the minimal sum in this case. Actually, should maybe not be quite so hasty, because I said you could easily do it, but notice that Z here is a function of 6 inputs, and we haven't done any Kernel maps with 6 inputs. Once you get a function of that many inputs, it's more convenient, rather than using the Kernel map, to use an alternative method called the Mccleskey method. We may talk about that at the end of this course, but we're not going to talk about it at this time. So don't worry about trying to prove that this expression here is indeed a minimal sum. You don't have to prove that, but I do hope that you'll be able to look at it and see that it makes sense. Let's now look at some problems for this lecture. Okay, so for the problems for lecture 17, all 3 problems, 17.1 through 17.3, refer to the circuit shown here. Notice that we have 2 2-to-1 multiplexers, and in this one we have Y selecting. We have the 2 input lines, I0 and I1. The output of that multiplexer goes into the 0 slot, you might say, of the second multiplexer. I2 goes into the second one, and the select line for that one has X. And the final output of that multiplexer is Z. And so the first 2 questions are, if X is equal to 0 and Y is equal to 0, what is Z? And the options are I0, I1, I2, or I0 ANDed with I2. And then the second question, 17.2, is, if X is equal to 1 and Y is equal to 0, what is Z? And you have the same options. And problem 17.3 will be given in class, but it will also be based on this same circuit diagram. So that concludes lecture 17, and good luck.